Welcome back to the Professor Insight podcast, the space where we explore the intersection of artificial intelligence, neuroscience, and emerging technology, and turn it into something practical for your business, your strategy, and your everyday thinking. I'm your host, Professor Billy. As always, a quick note before we begin. This podcast is fully powered by AI tools, from content creation to script writing and voice generation. And yes, what you're hearing right now is a voice clone of me, brought to life with full human oversight and manual curation. Now, let me start this episode with a question. What do large language models and students sitting an exam have in common? Here's the surprising answer. When faced with a tough question they don't know, they both tend to guess. And just like a student bluffing their way through an essay, language models often produce confident, fluent answers that are flat out wrong. We call these errors hallucinations, and they remain one of the thorniest challenges in AI today. In this episode, we're digging into fresh, unpublished research from OpenAI and Georgia Tech titled Why Language Models Hallucinate. And here's the key point. Hallucinations aren't some mysterious glitch in the machine. They're a natural byproduct of how these systems are trained and tested. The study shows that the very statistical methods used in pretraining, methods designed to make models sound fluent, also make them prone to generating plausible falsehoods. And once we put them through post-training and benchmarking, things actually get worse. Why? Because our evaluations, much like school tests, punish hesitation and reward confident guessing. This matters right now because we're deploying AI into classrooms, boardrooms, hospitals, and even legal systems. If the default behavior of these systems is to guess rather than admit uncertainty, that's not just a technical quirk, it's a trust issue. Imagine an AI confidently giving you the wrong medical information or inventing a citation that doesn't exist. The researchers argued that as long as benchmarks continue to reward accuracy without rewarding honesty about uncertainty, hallucinations will persist. So today, we're going to unpack where hallucinations come from, why they're so persistent even in cutting-edge models, and what can actually be done to fix them. We'll look at the statistical roots of the problem, the socio-technical traps built into current evaluation, and the provocative solution the authors propose, rethinking how we score AI altogether. Now, understanding why language models hallucinate isn't just an academic exercise. It's about building more trustworthy AI and reshaping the rules of the game so that saying "I don't know" is finally valued as much as guessing. Now, let's dive into the conversation about AI hallucinations.
We've all been amazed by AI lately, haven't we? I mean, you see them composing music, writing pretty complex code, summarizing dense texts. It's genuinely impressive stuff.
Absolutely. The pace of development is just staggering.
Well, sometimes they just make things up. Completely plausible, confidently delivered falsehoods. We call them hallucinations, and honestly, they're one of the biggest challenges for anyone using AI today.
Yeah, that's a great way to put it. It erodes trust.
Exactly. Take this example from the research we looked at. Someone asked a really advanced model for Adam Talman Kalai's birthday. And they were specific, DDMM, if known.
Okay.
The model gave 3 different dates, 0307, 1506, and 0101, all wrong. And it couldn't even just say, sorry, I don't have that information.
Wow. Just kept guessing.
Right. So today we're taking a deep dive into why this happens, and maybe more importantly, how we can actually start to fix it.
And what's really fascinating here is that these aren't just like random glitches or the AI trying to be creative.
Right.
Our sources, they argue pretty strongly that these hallucinations are a very specific kind of error. They stem from these fundamental statistical pressures during the training and, crucially, the evaluation stages.
Statistical pressures.
Yeah.
So less like imagination, more like math.
Kind of, yeah. It's less about the AI being inventive and more about it being optimized to be a really good but often way too confident test taker.
A test taker.
Exactly. And understanding this, it isn't just for the AI developers building these things. It's critical for you, the user. If you know the underlying reasons, you can interact with these tools much more effectively and, critically evaluate what they tell you. It makes the whole experience more reliable.
Okay, let's unpack that then. So our sources are saying hallucinations aren't some deep mystery. They actually start pretty simply from errors in what's called binary classification and right back at the beginning in pre-training.
That's the core idea. Binary classification, just think of it as the AI constantly making internal yes-no decisions based on patterns it's learned.
Like, is this text plausible, or does this fit the data I've seen?
Precisely. Is this a valid language model output? That's the implicit question.
Okay. And here's the bit that really surprised me. The sources say even if the training data was perfect, like absolutely error-free, the models would still make these errors.
Yeah, that's the kicker, isn't it? It's baked into the statistical objectives they're trying to meet during that pre-training phase. It's a consequence of the math involved in generation versus classification.
So tell me more about this is it valid problem. How does that work?
Right, so this is it valid, or for problem, as the researchers call it, is this implicit binary classification task happening constantly during pre-training. The model sees vast amounts of text and learns to predict the next word, essentially learning what looks right.
Okay.
But here's the key insight. Actually generating a valid, correct response is mathematically much harder than just recognizing if a given response is valid or not.
Yeah.
Think about writing an essay versus grading one. Grading is easier, right?
Yeah, definitely easier to spot errors than to write perfectly.
Exactly. And the sources show this direct mathematical link. The error rate when the model generates text is roughly double its error rate on just classifying text, using that is it valid logic.
Double. Wow. So even if it's pretty good at spotting fakes, it's twice as likely to create them itself.
That's the statistical reality. It implies there's this sort of fundamental ceiling on how truthful an LLM can be, purely based on this generative versus classification difficulty. If it can't perfectly tell fact from fiction in that binary sense, it's statistically bound to produce plausible-sounding nonsense sometimes.
Okay, that doubling factor is really something. So what causes these initial misclassifications in the first place? What makes it hard for the model to get that is it valid check right?
Well, one major factor they identify is arbitrary fact hallucinations. Think about facts like birthdays or specific historical dates or, the capital of Burkina Faso.
Right, things that don't follow a neat pattern.
Exactly. There's no inherent rule or structure connecting Adam Talman Collide to January 1st or whatever his actual birthday is. The knowledge just isn't consistently present or learnable in a patterned way across the massive training data set. This relates to what researchers call epistemic uncertainty. The necessary information just isn't structured in a way the model can reliably generalize from.
So it's like trying to learn grammar versus memorizing a phone book.
That's a good analogy. And they introduced this concept, the singleton rate, which is quite revealing.
Singleton rate.
Yeah, it refers to facts that appear only once in the entire pre-training data set. The statistic they found is startling. If, say, 20% of birthday facts are singletons, they only appear once in billions of documents. Then you can expect the base models to hallucinate on at least 20% of birthday-related queries.
Whoa. A direct link between how rare the fact is and how likely the model is to just make something up.
Precisely. It highlights how sensitive these models are to the frequency and consistency of information in their training data. If it only saw it once, it's basically guessing based on a very weak signal.
Okay, so rare facts are a big problem. What other reasons are there for errors during this pre-training phase?
Another significant factor is what the paper calls poor models. Now, this doesn't necessarily mean the LLM itself is, bad overall.
Okay.
It means its specific architecture or how it represents information internally might just not be well suited for certain types of tasks. The letter counting example is perfect here.
Ah, yes, the DeepSeek example.
Right. You asked DeepSeek v3, a really powerful model. How many Ds are in DeepSeek? It kept giving answers like 2, 3, 6, 7. The right answer is 1, obviously.
Clearly not its strong suit.
But then DeepSeek R1, a model specifically designed for reasoning, nails it. It counts them correctly and even explains how it counted them step by step.
So same data, different model architecture, different result.
Exactly. It suggests the V3 model's way of processing the word, maybe breaking it into tokens rather than seeing individual letters easily, just wasn't equipped for that specific kind of counting task. The model's internal worldview wasn't right for the problem.
Makes sense. It's not just the data, but how the model is built to interpret it.
Yep. And then you have other factors too. There's computational hardness. Some problems are just incredibly complex, maybe too hard even for current computing power to solve reliably, so the AI struggles.
Like really complex logical reasoning, maybe?
Could be. Or predicting highly chaotic systems. Then there's distribution shift. That's when the question you ask is really different from the kind of text the model was trained on.
Like asking a legal AI to write rap lyrics.
Kinda, yeah. Or the classic riddle, what's heavier, a pound of feathers or a pound of lead? It trips up models sometimes because the phrasing is unusual compared to typical factual statements.
Right, it breaks the expected pattern.
And finally, the one we all know, Garbage in, garbage out, or gee, I go. If the training data itself contains errors, biases, conspiracy theories, outdated information, well, the model is likely to learn and repeat that garbage.
So it learns our mistakes, too.
Unfortunately, yes. It holds up a mirror, flaws and all these things, arbitrary facts, model limitations, complexity, data shifts, bad data, contribute to those initial errors baked in during pre-training.
Okay, so we've established that LLMs are kind of statistically prone to making errors right from the start during pre-training. But then they go through more training, right? Post-training, fine-tuning, RLHF, reinforcement learning from human feedback.
Correct. Those stages are designed specifically to align the model better with human expectations, improve helpfulness, and reduce harmful or incorrect outputs.
So why do these hallucinations, these confident falsehoods, still persist, even in the most advanced, heavily fine-tuned models we use today? This is where it gets really interesting, doesn't it?
It really does. Because the explanation our sources offer shifts from pure statistics to something more socio-technical. It draws this fascinating parallel to something very human.
Which is
Taking an exam.
taking an exam. How does that relate to AI making things up?
Think about it. You're taking a multiple choice test. You're not sure of the answer. What do you often do? Guess. Especially if there's no penalty for a wrong answer.
Exactly. You guess to maximize your potential score. Or maybe it's an essay question, and you don't really know the details, so you bluff. You write something plausible, hoping for partial credit.
Okay, yeah, I can see that.
Well, the argument is that language models are, in essence, always in that test-taking mode. They're constantly being evaluated against benchmarks.
Right, the leaderboards and stuff.
Precisely. And most of these benchmarks use a simple binary scoring system. 1 point if the answer is deemed correct, 0 points if it's incorrect, or if the model expresses uncertainty, like saying, I don't know, or IDK.
Wait, so saying I don't know gets the same score as giving a completely wrong answer?
In many, many prominent benchmarks, yes. 0 points either way. Under that system, what's the rational strategy if the model is uncertain but thinks there's some chance its guess might be right?
Guess. Always guess. Because saying I don't know guarantees 0 points, but guessing gives you a chance at 1 point. Bingo. This creates what this paper calls an epidemic of penalizing uncertainty. Imagine you have two models. Model A is programmed. To be honest, if it's not sure, it says I don't know. It never hallucinates.
Okay, the ideal honest AI.
Then you have Model B. It's pretty similar in capability to Model A, but whenever it's uncertain, it takes its best guess. It will hallucinate sometimes. Which model do you think scores higher on these standard 0-1 benchmarks?
Model B, the guesser. Because all its correct guesses get points, and its wrong guesses get the same 0 points that Model A gets for honestly saying, I don't know.
Exactly. Model B will consistently outperform Model A on most current benchmarks. The system effectively rewards guessing and penalizes caution.
Wow, that's a massive insight. So the problem isn't just that we haven't figured out how to stop hallucinations technically, it's that the way we measure AI progress actually encourages them.
That's a huge part of it. The issue isn't a lack of specific hallucination tests, though those exist. It's that the mainstream evaluations, the big ones that drive development and funding and get all the attention, MMLU, GPQA, SWE bench for coding, things like that.
The ones everyone quotes.
Yes. Those predominantly use this strict binary grading. No points for I don't know. And get this, some benchmarks, like one called Wild Bench, might even score an I don't know, lower than an answer that contains factual errors, but is otherwise, fluent or helpful sounding.
You're kidding. It's worse to admit you don't know than to be subtly wrong.
In some evaluation setups, yes. The incentive structure is basically screaming at the AI, never admit uncertainty, always bluff, sound confident.
It's like we've designed an education system that rewards confident bullshit bluffing over cautious honesty.
That's a pretty apt, if blunt, comparison. It means that even as developers try to reduce hallucinations through fine-tuning, the underlying evaluation system is constantly pushing back, reinforcing the very behavior they want to eliminate.
So it's a fundamental incentive mismatch.
Precisely. And for you, the user, this is critical. When an AI gives you an answer super confidently, remember this dynamic. It might be correct, sure, but it might also just be playing the game it was trained to win, avoiding the 0 points that come with saying, I don't know. It's optimized not to leave a blank space on the test.
Which means we as users have to be even more critical of the outputs, especially when the stakes are high. We can't just assume confidence equals competence.
Absolutely. That confidence might just be an artifact of the evaluation pressure cooker it was developed in.
Okay, so if the problem is deeply rooted in these misaligned incentives from the way we evaluate models, then the solution has to tackle that directly, right? We need to change the test.
That's exactly what the research proposes. And the solution is statistically sound, but actually quite straightforward conceptually. It involves introducing explicit confidence targets into the evaluations themselves.
Confidence targets, how does that work? Is it like asking the AI to rate its own confidence?
Not quite asking it for a number, but changing the scoring rules so that its behavior reflects its confidence. Think back to exams you might have taken where you actually lost points for wrong answers, more than you would for just leaving it blank.
Oh yeah, negative marking. Makes you think twice before guessing wildly.
Exactly. It forces you to consider your actual confidence level. The proposal here is similar. For each question in a benchmark, you'd add a clear instruction, something like, answer only if you are more than, say, teat confident, where it's a threshold, like maybe 0.75 or 75%.
Okay.
And then you change the scoring. Mistakes of penalized t divided by 1 minus t points, while correct answers get 1 point. Saying, I don't know, gets 0 points.
Whoa, okay. There's some math there.
Yeah.
T, 1T. Why that specific penalty?
It seems complicated, but it's actually the precise mathematical penalty needed to make it optimal for the AI to say, I don't know, if its internal probability of being correct is below that threshold t.
So, if we set the confidence threshold 10 at 0.75, and the AI calculates its chance of being right is only, say, 60%, the math works out so that guessing is expected to lose points on average, while saying, I don't know, gets 0.
You got it. Suddenly, guessing isn't the best strategy anymore if you're not confident enough. Abstaining becomes the rational choice below that threshold. It makes signaling uncertainty not just acceptable, but mathematically advantageous in the right circumstances.
So it's not just about punishing wrong answers, it's about creating a scoring system where honesty about uncertainty is actively rewarded by avoiding penalties.
Exactly. And this leads to what the researchers call behavioral calibration. The model learns to make the right decision, answer, or abstain based on its internal confidence level, rather than just always trying to maximize the chance of getting that 1 point, regardless of risk.
It's about aligning its output behavior with its internal state of knowledge.
Precisely. It's less about it telling you, I'm 70% sure, and more about it acting appropriately given that 70% certainty, according to the rules of the evaluation.
And the crucial point here, which the paper stresses, is that this change needs to happen not in some new, separate hallucination benchmark that nobody pays attention to,
Right.
but in the mainstream evaluations, the GPQAs, the MMLUs, the SWE benches, the ones that actually drive the industry.
But that's the key to shifting the entire field's incentives. If the main leaderboards start rewarding calibrated uncertainty, then developers will optimize for it. It makes honesty a competitive advantage.
And by making, I don't know, a valid, non-penalized option in the core tests, it probably makes any additional specific hallucination tests much more effective too, right? Because the baseline behavior is already more cautious.
Absolutely. It creates a foundation of better behavior upon which more specialized evaluations can build. It fosters genuinely more trustworthy AI systems from the ground up.
So what does this mean for us, for the average user interacting with these tools day to day?
Well, if these kinds of evaluation changes are adopted more widely, it could mean a future where the AI you're using is significantly more honest to its limitations.
So I could potentially ask a question and add, only answer if you're highly confident.
And the model, having been trained and evaluated under these new rules, would actually be incentivized to respect that instruction. If its confidence is below the implicit or explicit threshold, it would be more likely to say, I don't know, rather than give you a plausible but potentially wrong answer.
That feels like a major step towards AI we can actually rely on more.
It really does. It moves us towards AI systems that aren't just, powerful pattern matchers, but also demonstrate a kind of pragmatic competence, understanding not just what information exists, but having a sense of how reliable that information is and communicating that appropriately, knowing when to speak and when to stay silent.
Okay, so wrapping this up, we've journeyed from the statistical inevitability of some errors during pre-training, even with perfect data, which is wild, all the way to how the tests we use to judge these models have inadvertently created an environment where bluffing is rewarded, causing hallucinations to persist.
A real journey through the AI life cycle.
It really is. And it shows it's not just some mysterious ghost in the machine making things up. It's a complex interplay of statistics, model architecture, data, and crucially, the incentives we create through evaluation.
Well put.
But the good news, maybe the most surprising part, is that a potential path forward isn't necessarily some incredibly complex new algorithm. It might be as simple, conceptually at least, as changing the rules of the tests.
Indeed, it's a socio-technical solution, really. Modify the scoring on the existing influential benchmarks to properly value expressions of uncertainty. Don't penalize, I don't know.
Make honesty the best policy, even for an AI.
Exactly. And that could fundamentally reshape how these models behave. It could lead to AI that feels much more transparent, more reliable, and ultimately more trustworthy. Imagine interacting with an AI that, like a truly knowledgeable expert, is confident when it has the facts, but readily admits, I don't know when it doesn't.
Yeah.
That feels like a different relationship entirely.
It really does.
This change, this shift in evaluation, could genuinely pave the way for a new generation of AI. One that's not just intelligent in processing information, but also reliable in how it presents it. Which leads to a final thought, really, for you listening. How would your interactions with AI change? How would the way you use these tools evolve if you could fundamentally trust them to signal their uncertainty accurately? What new possibilities would that open up?
That's a great question to ponder. Thanks for joining us on this deep dive into the fascinating and sometimes frustrating world of LLM hallucinations. We really hope this gives you a clearer picture and maybe some new ways to think about how you engage with AI every day.